So good morning, everyone. We are going to wait still maybe 1 minute to see if more people is joining. Good morning, good afternoon, or good evening, depending on your time zone. Okay, so I think we can slowly start. So as I said, good morning, good afternoon, or good evening, depending on your time zone. My name is Marcos Curti. I'm from University of Vigo in Spain, and I'm going to chair this session. So please don't forget that if you have any question, then you can either raise your hand and then I will unmute your microphone, or you could just write your question in the Slack channel. So for me, it's a pleasure to introduce today Mirko Pittaluga. He is a researcher at TOSHIBA, and they have been doing fantastic work on extending the distance of QKD far beyond what was believed possible without quantum repeaters. So his talk today will be about experimental repeater-like quantum communications over 600 kilometers of optical fiber with dual band phase stabilization. So Mirko, the stage is yours.
Thank you very much, Marcos, for the introduction. And please let me know if there is any problem with the audio or with the video during this presentation.
We hear you well.
Fantastic. Hi, everyone. I'm going to introduce myself again. My name is Mirko Pittaluga. I'm from TOSHIBA Europe. And I would like to start my presentation by thanking the organizer for giving me the opportunity to present at this year's QCrypt conference. Yet for another year, the level of the conference is extremely high with a large number of great contributions, and I'm very glad to be here today. But let's now begin by reading again the title of my talk, which is Experimental Repeater-like Quantum Communication over 600 kilometers of optical fiber with dual band phase stabilization, which I realize is a very long title. And for this reason, I think it makes sense to explain its different bits and pieces to clarify what I'm going to talk about today. So the first bit is the experimental one, because I'm going to talk about experimental results that we obtained over the last couple of years at TOSHIBA. The second bit is the repeater-like, and these refer to the fact that I'm going to talk about the implementation of the twin field QKD protocol, which we were able to execute for the first time over 600 kilometers of fiber. And in order to achieve this result, we had to introduce a new stabilization technique that we call the dual band phase stabilization. This presentation will be divided in 4 parts. At the beginning, I will give an introduction to the limitation of point-to-point quantum key distribution. Then I will give an introduction to the twin field QKD protocol for those of you that are not very familiar with the protocol. And then I will talk about the experimental aspect of the protocol implementation. All this introduction part will be quite long, thanks to the quite a lot of time that I have available today. And then just towards the end of my talk, the last 15 minutes, I will talk about the experimental results that we obtained in the recent years at TOSHIBA. So let's begin by talking about the limitation of point-to-point QKD. It is, in this case, probably useful to clarify what I mean by this term, with which I intend quantum communication protocols where the users that want to establish the communication are located at the ends of an interrupted communication line characterized by a length L and attenuation coefficient alpha. Since in quantum communication, the information is encoded in quantum carriers and cannot be straightforwardly amplified, and due to the unavoidable losses of the quantum channel, then we have that only a fraction of the information encoded by Alice will be received by Bob. The transmission of the channel is often referred to with the letter eta, and it decreases exponentially with the channel length. And since in QKD, we need some quantum material to execute the protocol, then, in an intuitive manner, it's already possible to realize that the QKD rate should scale approximately with the channel transmission. This observation could be summarized by this relation here. So we have that the combined effect of the channel loss together with the no cloning theorem that applies to quantum states fundamentally limit the range of QKD. This fact can be now well visualized by looking at this graph here, where we plot the results of state-of-the-art QKD experiments executed over the past 10 years. And you can well notice that the secret key rate to losses here, the trend, decreases linearly with the channel transmission. This observation has been formalized in a recent work by Pittaluga and co-authors, which is reported here, where they gave a formal and ultimate quantification of the capacity for a point-to-point communication, QKD communication. This limit is known as the secret key capacity bound. So this acronym here, or plot bound, from the name of the authors that introduced it. And basically what this limit and bound tells is that it is not possible to do point-to-point QKD that overcomes this red line. Clearly, at this point, a question arises naturally, which is if there is a practical way to overcome this bound and therefore execute QKD at high channel losses or high channel, long channel distance in a practical manner. And this would be the topic of my next slide. Well, the answer to this question is yes, in fact. And the only way to overcome the plot bound is by the use of quantum repeaters. And I think that it is at this stage, again, useful to specify what I mean by quantum repeaters. And for this, I will use the definition given in the reference that I'm showing now at the bottom of this slide. So in an information theoretic sense, a quantum repeater is any type of middle node between Alice and Bob that helps their quantum communication by breaking down their original quantum channel into different quantum channels. This can be visualized now by this new figure, where the communication line between the two communicating users, Alice and Bob, is broken down into shorter pieces by the repeaters placed along it. And as you can see, the distance between the repeaters is clearly shorter than the overall length of the channel. It is important to notice here that there are several types of quantum repeaters, which can be grouped by their properties. And this is exactly what we're going to do in the next slide. So quantum repeaters can be characterized by looking at their most important characteristic, which is their degree of security and the distance that they can help to achieve. By starting by considering the communication distance, a first distinction can be made between repeaters that allow us to overcome the plot bound, that is the theoretical limit that we introduced before, and those that cannot. So we have that the repeaters architecture that allows to overcome the plot bound are called effective repeaters, while the ones that do not allow to overcome the plot bound are considered to be non-effective quantum repeaters. And at this stage, we can introduce the simplest class of quantum repeaters architecture, which is the trusted node architectures. This architecture basically works by implementing point-to-point QKD between all the nodes along the channel, and it allows to overcome the plot bound with a suitable number of nodes. And it is an interesting approach, but the security of this type of architecture is considered to be quite low because in this architecture, the two end user, Alice and Bob, will have to put, I believe, unconditional trust on the intermediate node, which is, well, it's not a great assumption if for a quantum secure communication. So we can now look at the next class of quantum repeaters, which is in a way considered to be the sacred grail of repeaters. And these are entanglement-based repeaters, which works basically by generating and distilling and distributing entanglement among the nodes placed along the line. Unfortunately, though, these devices are not yet feasible with the current technology. But luckily, there is another subclass of entanglement-based repeaters, which are the measurement-based repeaters, which are repeaters that are configured as a 3-node networks, as the one that I'm showing here in the slide, where the relay breaking the channel, the channel length between Alice and Bob is the measurement station. Example of these type of repeaters are measurement device independent, QKD or MDI QKD, but also measurement assisted, memory assisted MDI QKD, or importantly, twin field QKD. That is one of the main topics that I'm going to talk about today. The important caveat here to notice is that MDI QKD, due to its functioning principle, constitute a non-effective quantum repeater, as it does not allow to overcome the clock bound, while these two protocols, so memory assisted MDI QKD and twin field QKD, they actually constitute an effective repeater. And in the next slide, I'm going to explain what this means on a practical level. So to do this, yes. So here we compare the experimental points shown earlier in the previous slide, alongside the plot bound that we introduced before. And also here we're showing the equivalent bounds for quantum communication aided by an increasing number of repeaters along the line. Here we can see that by plotting alongside these curves, the theoretical and experimental secret key rate for TF-QKD, we can appreciate that its secret key rate scaling with distance goes with the square root of the channel transmission, which is exactly the same, the one of our communication line aided by a single node quantum repeater. And importantly, we can see that the even in the realistic implementation of the twin field QKD protocol, where we have that we can overcome the plot bound at already 60 dB channel attenuation. Importantly, it's worth noticing that TF-QKD is the only readily implementable protocol overcoming the plot bound at high attenuation. And I think that the take-home message here from this introduction is that TF-QKD is the best tool that we have at hand at the moment for long distance and high attenuation fiber-based QKD system. Okay. I think that now we are ready. Now that we have given an overview of the TF-QKD protocol, we're ready to talk about its implementation aspect. So in this scheme here, I'm showing a simplified diagram of a TF-QKD setup. And on the right, I'm highlighting its most important implementation properties. So here I'm talking about the encoding that is using TF-QKD, which is done on the phase of the optical fields. The type of detection done at the middle node is a first order optical interference, which is detected through single photon detection. And due to this particular strategy of encoding and interference, then we have the secret key rate of the protocol scales with the square root of the channel transmission, as we mentioned earlier. Importantly, in this configuration, we have that this protocol also removes all the detector side channels, and the detection in this scheme can be made at the central node by an untrusted relay. I think that it is useful to compare this implementation aspect of TF-QKD with those of MDI QKD, which I think is a probably better known protocol within the community. And the most notable differences here between the schemes are the lack of a phase locking mechanism between the users and the encoders in the MDI QKD scheme, and also the different setup of the central node in MDI QKD. The differences also are in the this different configuration depends on different types of encoding and interference detection that is used in MDI QKD, which is in terms of encoding a single photon encoding and by both the users, while the type of interference and detection at the central node is a second order Hong-Madden interference, and where it can be measured through a 2-photon coincidence measurement. And these factors together, and more specifically the fact that for a successful measurement in MDI QKD, we need to receive simultaneously a photon from both the users. We have that the secret key rate scaling for MDI QKD goes with the linearly with the channel transmission rather than with the square root of the channel transmission. But importantly, similarly to TF-QKD, also MDI-QKD removes detector side channels, and the detection can be made by an untrusted relay, an untrusted user. And I think it's worth mentioning that this was actually the first protocol introducing this feature in QKD. So these two protocols were introduced in the references that were reported here at the bottom of the slide, with the TF-QKD protocol introduced in 2018 by Marco Luca Marini and other researchers at TOSHIBA. And despite being quite a novel protocol, there has been a tremendous amount of research on this protocol over the recent years that I'm going to summarize in the next slide. So here I'm showing only some of the theoretical and experimental contribution made on the subject in the recent year, and I'm leaving this slide here for a few seconds more if there is anyone in the slide that is interested in understanding a study a bit more, so that they can take a screenshot of this page for later use. The only thing that I would like to highlight here is that while the original TF-QKD protocol proposal wasn't unconditionally secure against all the type of attacks, luckily many protocol variants have been proposed over the past years, which solve this aspect. And now we have versions of the protocol that are unconditionally secure and that are well accepted within the community. Okay, I think that it's finally now time to focus on the experimental challenges associated with the experimental implementation of the protocol. And I would like to do this by comparing the challenges of implementing TF-QKD with those of implementing a standard QKD protocol. The challenges for implementing a standard QKD protocol are, well, the single photon generation and manipulation, the quantum channel stabilization in terms of polarization and time alignment, for example, and the single photon detections. These challenges have been subject of study for many years now and have today well-established and practical solutions. And to these challenges, though, TF-QKD adds the difficulties related to the control of the optical phase of the setup, which has to be maintained under control given that the information in this protocol is encoded in the phase of the optical fields. So experimentally, we have in fact to control the phase noise of the system, which, as I'm showing in this formula here, has two main contributions. The first contribution arises from the frequency difference between the user's lasers, and it requires basically the phase locking of distant laser sources. And the second contribution arises from optical path length fluctuation. And this can be tackled and solved by adopting some phase stabilization strategies for the quantum channel. More in the detail, we have that the techniques that are nowadays used for solving the first problem, so the phase locking of the distant sources, are optical injection locking generally, and also optical phase lock loops. While for the phase stabilization of the quantum channel, the techniques are passive or active stabilization, which the last one can be done both in post-processing or in real time. In my opinion, I think that the phase stabilization, so this challenge here, is the most difficult of these two challenges. And this is actually what we're going to focus in the next slide. So I think that a way to understand the problem of phase fluctuations is considering the phase noise of a large Mach-Zehnder interferometer, which is reported here on the top of this slide. So we have that in a Mach-Zehnder interferometer, the intensity fluctuations at its output are related to the differential phase shift between the two arms of the interferometer. And basically by measuring this fluctuation for a system that is hundreds of kilometers large, like reported in this graph here, and it's worth mentioning or reminding that hundreds of kilometers is still the dimension and the length at which the properties of TF-QKD becomes relevant. By making this measurement on a Mach-Zehnder interferometer, we have that the phase drift introduced by the long communication channel scales with the square root of the channel length. And if we consider 500 kilometer long channel, for example, we have that the phase drift is in the order of several rad per millisecond, or equivalently several thousands of radian per second. And clearly, stabilizing such a rapid phase drift is a clearly challenging task. And different strategies have been developed to achieve this over the recent year, which I'm going to discuss in the next slide. So a first distinction between the stabilization strategies can be made between passive and active compensation. In passive compensation, the problem of the phase stabilization is solved by adopting a very specific experimental configuration, which is that of a Sagnac loop, along which are placed the communication parties. This is a very clever solution, in my opinion, as it removes completely the problem of compensating for the phase drift. But it is, in a way, inherently limited in its application by its topology, which is the one of a of a loop. And to my knowledge, is also the scaling properties of this type of configuration have yet to be fully understood and demonstrated. But for those of you interested in having more information on this type of configuration, I recommend having a look at the poster session where a poster about this type of configuration is presented in the poster, and the poster is the number 132. But let's now talk about the active compensation strategy, which can be, so this one, which can be further divided into two categories. So we can have noise compensation that is done in post-processing, or the compensation can be done through active noise cancellation. So the compensation done in post-processing generally works by time multiplexing a bright reference pulse along the the encoded quantum signal. The reference signal is used to track the instantaneous phase difference between the two arms of the system. And this information is then taken into account during the post-processing phase of the protocol. And this type of stabilization has been used in the references reported here. And in this figure here, I'm showing the typical pattern using this type of solution, where we have that the quantum signal, that is the blue one here, is time multiplexed together alongside, I should say, with the bright reference pulses used for the channel, the phase tracking in a way. And the final type of phase stabilization is the active noise cancellation. And in these cases, we have a feedback system that is active during the whole duration of the protocol. And this feedback system corrects the phase shift introduced by the communication channel. This is the stabilization strategies that we use in our works, and also in this has been used in this other reference here. And it is important to notice here that while for the noise compensation done in post-processing, the reference signal were always, so far at least, time multiplexed with the signal. In active noise cancellation, the reference signal can be either time multiplexed or wavelength multiplexed with the signal. But we will discuss this better later, and will be the subject of future slides. So, yes. Well, yeah, I should have stopped that one. Well, in this slide, I'm going to present the most relevant recent advances for long-distance quantum communication obtained in TF-QKD and standard QKD. So I will start by comparing the state-of-the-art result obtained for QKD, which was obtained in this reference here by Boron in 2018, and the results obtained for lab-based QKD experiment. So all these experiments were obtained in the lab. And as you can see, lab-based TF-QKD demonstration reached the 500 kilometer of distance, which is roughly 100 kilometers more than the previous state-of-the-art for standard QKD, which is already a considerable extension of the distance for QKD. But I think that even a more impressive result is the comparison between the state-of-the-art for standard field trial, for standard QKD field trial implementation, which I'm plotting here, the longest distance that I could find in literature, found in this reference here, so by Womford in 2021, And it is possible to compare this with the state-of-the-art result for field trial TF-QKD, which were executed at the beginning of this year, where the authors were able to push the limit for field trial QKD to roughly 500 kilometers. And this is basically a 400-kilometer improvement over the previous state-of-the-art, which is a really impressive result, in my opinion. All these results were obtained by groups based in China, led by the professor Zhang Weipan. And all these experiments have several aspects in common. So they have the same phase stabilization strategy, which is done in post-processing. And in all these experiments, the reference signal is time multiplexed with the encoded quantum pulses. These stabilization methods have some drawbacks, which are related to the fact that the time multiplexing of the reference signal reduces the clock rate of the quantum pulses. And we also have that the bright stabilization signal at the same wavelength of the encoded signal introduce Rayleigh noise, which we will see later, better in the next slide, limit the maximum distance achievable with this configuration. But for those who are interested in having more information about all these experiments, I recommend to tune in tomorrow at 2:30 p.m. for the talk by the professor Zhang Weipan, which I believe is going to talk about these results here. So I think that after this very long contextualization, we have now all the elements necessary to understand the contribution of our work. And as I mentioned earlier, the biggest factor limiting the distance and secret rate for the discussed TF-QKD implementation is double Rayleigh scattering. So this problem was highlighted in the work reported at the bottom of this slide, where the authors calculated that the Rayleigh scattering introduced in the communication channel by the bright reference becomes a limiting factor for experimental TF-QKD around 500 kilometers. And the problem with this type of noise is that it is very difficult to filter it out, as it is at the same wavelength of the signal of interest, and it is uniformly distributed time. So given this problem, at TOSHIBA, we started exploring ways to execute the stabilization in a different manner. And we realized that if we moved the bright reference signal from the same frequency as the quantum signal to a different one, the noise affecting the signal would become the Raman scattering rather than the Rayleigh scattering. And as you can see now from the simulation here on the right, the Raman scattering introduced a much lower noise on the detector compared to the Rayleigh scattering. And here in this graph here, we have that the Rayleigh scattering is the purple one, while the Raman is the brown one. And we can see that the Rayleigh scattering has a much worse scaling with the channel length and with the communication distance, basically. And in the next slide, I will explain how a stabilization system based on two wavelengths works. So here I'm showing a Mach-Zehnder interferometer that is similar to the one that I've shown a few slides ago, with a difference here that now we're injecting two different optical signals into the system. So we have laser 1 emitting at lambda 1, and then we have a laser 2 emitting at lambda 2. And these two wavelengths are quite close in the optical spectrum. It is important to notice here that the two signals travel down the same path, and these two wavelengths have different purposes, which are summarized in this table here. So we have that the wavelength lambda 2, which is also called the reference wavelength, has a high intensity. It is not modulated, and its function is that of giving information for executing a fast stabilization on the communication channel. And the fast stabilization is done through a fast feedback, which is represented at the top of this figure here through the stage 1 feedback system here on top. Then we have the second wavelength. So, well, the other wavelength, which is lambda 1, which is called also the signal wavelength, which is generally a low, well, it has a lower intensity. It is modulated both in intensity and phase. And the purpose of this wavelength is that of giving information for a second feedback, which is the stage 2, also called the stage 2 phase compensation feedback, which is much slower than the other one, and which acts, important to notice here, this feedback acts only on lambda 1 wavelength, while the other feedback was acting on both the wavelengths simultaneously. And importantly, lambda 1 is also used for the key generation. So with this type of setup, we can now send a bright reference over lambda 2 for stabilizing the phase of the system and remove the detrimental effect of the Rayleigh scattering on the encoded signal. And in the next slide, we will characterize the performance of a stabilization system based on this dual band principle. So here on the left, I'm showing a block diagram of the feedback system that we use in our experiments. So at the top, we have the stage 1 feedback system, which operated at a very fast speed, so 200 kilohertz. At the bottom here, we have the block scheme of the stage 2 feedback, which operated at only 20 hertz. While on the right here, I'm showing the characterization of the effect of this feedback on the wavelength that you use for the quantum signal. So we have in purple the unstabilized signal, and as you can see, the unstabilized signal is drifting so fast that if we look at its intensity fluctuation over a timescale of 5 seconds, we are not able to distinguish the interference fringes. We're able to see the interference fringes only if we zoom into a 5 millisecond timescale. And we can characterize the phase drift of the unstabilized signal, and we measure that it's in the order of 12,000 radian per second. At this stage, at this point, if we start the stage 1 stabilization, so the fast one, we have that the signal goes from the purple one to the orange one. And you can see that the stabilization is quite effective, as now the orange one drifts much more slowly, and we can follow the phase drift over a time scale of 5 seconds. And if we go and look at the phase drift of the orange signal, we see that the phase drift is in the order of 2 radian per second, which is almost 4 orders of magnitude lower than before. But as you can see, the stage 1 stabilized signal, which is stabilized only with this feedback system here, has still some fluctuation, and this fluctuation can be removed by the second stage feedback, so the slow one. And when we activate it, we go basically from the orange signal to the green one here. And we can see that the green signal is basically fully stabilized. And we can appreciate it by looking also at the distribution of the phase angle measured over this time scale, so 50 seconds. And we can see that while the orange signal is basically, the phase for the orange signal is basically equally distributed over the pi phase range, the green signal is very well centered at a fixed position, which is half pi. So now we can see how a TF-QKD system using this type configuration looks like. And this is the experimental setup that we use for our experiment. I'm going to highlight the different pieces of this of the experimental setup. So we start here at the middle, looking at the laser sources, which are located at the central node. We have laser 1 and laser 2 emitting lambda 1 and lambda 2, which are then combined together by a beam splitter and sent to the user through 2 service channels. Along the service channels, due to the high losses that are associated with the long length of this channel, each channel is roughly 300 kilometers long, we had to place some classical optical amplifier to amplify the signal and increase its intensity. Once the signal encoded at the central node reach the user station, well, then they are demultiplexed. And while lambda 2, that is the signal used for the stabilization, is looped back, then we have that the lambda 1, that is the signal used for the encoding of the protocol, is regenerated through 2 OPLL setup. This regenerated signal is then encoded by passing through 2 encoders, one for each user, which has density modulators, phase modulators, and polarization controller inside it. And then the signal is back again multiplexed together with lambda 2 and sent down to through the quantum channel. Once after traveling the quantum channel, the 2 signals reach the central node where they interfere at the central beam splitter here. And we have here also the action of the 2 feedback systems that we saw before. So the fast one acting on both wavelength, and then we have the slow one acting only on lambda 1. And the key elements I think that is useful to highlight here. of this setup is that the two wavelengths here are traveling together through the communication channel or quantum channel. We have two feedback systems, a coarse one and a fine one, to compensate for the phase drift. And the advantages of using this strategy compared to the other strategy used by previous group is that the protocol rate, in our case, is not affected by the stabilization signal. And we do not have anymore the elastic scattering from the reference signal hinder the quantum signal. And thanks to these two advantages, we can obtain the result that I'm showing in this graph here. So our results are the one at the top on this of this graph here, and I'm comparing them with the points and the data that I shown in a past slide. So we have that our data are the ones that are fully colored, and while the empty one are the previous state-of-the-art results. And experimentally, the data that we obtained with the setup that I shown in the previous slide are the ones that are marked with a star. And the one marked with a circle are obtained with a slightly different setup that was asymmetric in shape, but that I'm not discussing here because of the time constraints, but maybe I can discuss later. And here we have two lines or two sets of results, the blue one and the red one. And the difference is that the blue one are obtaining the asymptotic regime, while the red one are obtaining the finite space regime. And it is important to notice here that thanks to the flexibility of our setup, we were able to test different protocols. We were able to test the QWERTY Zuma-Low protocol and also the SEN-NOD-SEN protocol, both in the classic SEN-NOD-SEN and also the SEN-NOD-SEN protocol aided by two-way classical communication. And well, I think that the biggest result and the biggest improvement factor over the previous result is that we are able, thanks to our techniques, to reach unprecedented communication distance of 600 kilometers. And we were able to overcome for the first time the 100 decibel attenuation of the channel. So, and I think that the last question that could arise by looking at these results here is whether our stabilization system is feasible in a real world operation. Well, I have an answer to this question that is reported here. So here I'm presenting the results obtained by INRIM, which is the Italian Institute of Metrology, with which we collaborated over the past years. And with their recent work, which is referenced here, well, we proved the feasibility and effectiveness of the dual band stabilization system over deployed fibers. The fibers used in this experiment are located in northern Italy, and they're part of the Italian quantum backbone network. And the location connected in this experiment are Bardonecchia and Sanchia, which are connected by fibers passing through Turin. And these locations were connected together by a 206 kilometer long fiber, which had a 65 decibel channel attenuation. It is important to notice here that there is a certain degree of asymmetry in this setup, which was allowed by the narrow line width of the laser used in this experiment. And the main result of this work are summarized on this graph here on the right, where it's shown the phase drift occurring on the channel when the dual band stabilization is active in red or inactive in blue. And here you can see that when the stabilization is active, the optical coherence of the signal is extended by more than 4 orders of magnitude. And this coherence of the system could be further extended practically to infinitely if we were adding a second slower feedback system as we did in our setup. And for those of you interested in having more information about this work, I recommend to have a look at the poster 96 in the poster area of the conference. The last thing that I would like to mention about this result is that it showed the usefulness and the ready adaptability of a fiber network, which is already in place and is part of a larger European fiber network used for time frequency dissemination. And this result highlighted, in my opinion, possible second use for this network, which could be very easily adapted for the implementation of phase-sensitive quantum communication tasks. And this is the subject of my last slide before heading towards the conclusion. So in this presentation, we talk about the implementation of a novel phase stabilization technique that allows us to reach unprecedented quantum communication distances over fiber. One thing that I would like to notice is that TF-QKD is not the only quantum communication task benefiting from a phase stabilized communication network. And in this slide, I'm showing a list of other tasks that could benefit from it as well, such as quantum secret sharing, quantum fingerprinting, phase-by-phase quantum internet, longer baseline telescopes, and also other QKD protocols, such as side-channel free QKD. So in this perspective, I think that the effectiveness of the dual band stabilization technique could be further explored and expanded to see if it could be adopted to other tasks. And this is something that we're currently looking into at TOSHIBA, and I'm personally interested to explore more in the future. With this, I'm heading to my conclusion for this talk. So in this talk, I talk about the implementation of a one node quantum repeater that allowed us to overcome the security capacity bound. We talk about our demonstration of QKD communication that for the first time overcame the 100 decibel channel loss, and that was executed over 600 kilometers of fiber. We introduced and demonstrated the feasibility of a dual band phase stabilization technique. We argued that this technique would be further future resource for phase-based quantum communication. And we proved the feasibility of this technique in real-world application in collaboration with IRIN. And with this, I would like to conclude while thanking also all the other members of the team at TOSHIBA that work on this project over the past couple of years. And I would like to say thank you very much for your attention and be very happy to receive any question.
Thank you, Mirko, for this very nice talk. So, as I said at the beginning, you can either ask questions by raising your hand or you can write them in the Slack chat. So, there is a first question here. I'm going to read it. It's a bit long. So, the twin-field QKD protocol allows to extend the quantum link between Alice and Bob. However, the distance between Alice and Bob is still limited. What should we do if we want to connect users with quantum link longer than twin-field QKD allows? It seems that natural solution is some kind of a trusted node network, similar to point-to-point QKD, but with each link based on twin-field QKD. What are the benefits of using more complicated twin field in such case instead of point-to-point QKD?
Okay, well, this is a very interesting question, and I think that maybe it could be useful to go back to a previous slide that I've shown, which is this one. Yeah. So I'm showing the types of quantum repeaters slide. Is that correct? Can you see that, Marcos?
Yes.
Fantastic. So the idea here is that the long-term solution for, well, basically unlimited distance type of communication would be having a full-fledged working entanglement-based type of entanglement-based repeater scheme. At this stage, in a way, the length of the communication line would be only limited by the properties and the qualities of the quantum repeaters that we have. But if we assume that we will have at a certain point in the future perfect quantum repeaters, then that will solve the problem. In the short term, well, as I said, the trusted node architecture is a feasible solution, definitely. And it is actually probably the most practical one if we wanted to build very long communication networks, such as the one that have been tested at the moment in Japan and in China, where I think that the network is over 2,000 or even 4,000 kilometers long. But yeah, the thing here, the caveat about the trusted node architecture is that we will have to put implicit trust on all the nodes along the communication line, which in certain uses is it's a legitimate assumption. For other use, maybe it's not such a great assumption for the users, whereby the users in this case I'm talking about Alice and Bob, so the one that want to exchange a secret message. In terms of using TF-QKD for longer distances, well, that's definitely a possibility in the sense that we extend the range for point-to-point QKD. But at the moment, as far as we know, the kind of configuration that allowed by TF-QKD is the one of 3-node networks, in the fact that it is fundamentally a measurement-based quantum repeater. So it would be possibly to think of having several measurement station scattered around, and that could connect to only points that are directly connected to the central measurement station. One thing that is very nice though about TF-QKD is that it being a measurement-based repeater and having this type of 3 nodes configuration, it is immediately suitable as it is actually MDI QKD to star-shaped network. So in this perspective, it is possible to think and project a large network, metropolitan network, or even kind of national networks in a kind of the definition of national in the European standard rather than the Chinese or American standard, where we have central locations where we have all the expensive bit of equipment. And then we have a multitude of users that send their signal to the central node, and that it can establish a secret key between them, which will be from the resources consumption and also economic point of view, quite a desirable configuration, because you will put all the most expensive equipment at a central node that can be shared by many, many users around the star. I'm not sure I answered this question, the original question, but I hope this had the person interested in it.
Yeah, no, I think it's fine. We have still a few more questions, so let's see if we have a bit time to go through them. One of them is from Vadim Makarov, and actually had the same question that is about one of your last slide. I think it was 17 or 18. You mentioned as a possible application what you call side channel free QKD. If you could give a bit more detail exactly what you mean or what you had in mind. Yeah, precisely here.
Side channel free QKD. Well, this is actually something. It's a protocol that has been put out on the archive at the moment. I'm not sure the protocol has been peer-reviewed yet, and I still have to go into detail about it. But it seems to me that it is a protocol that has a configuration similar to TF-QKD in the sense that it requires phase stabilized channel for it to work. And well, from the claim of the authors was that it was completely side channel free, and I didn't go into detail. So
I'm a co-author, so I didn't know you meant that paper. Okay, then I know what you mean. So yeah, it has been published in Physics Review Apply.
Okay, sorry.
So, okay. I didn't know you meant that protocol. So that's clear. So we have another question. Is from Tobias Guerin. He is saying, well, thank you very much for the talk, very impressive results. And he's wondering, what happens if an eavesdropper attack the signal used for phase compensation? Is there any problem there?
Yeah, I'm hearing a kind of a noise on the background. I'm not sure if someone unmuted himself. I'm not sure who is. Okay.
Now it's gone.
Now it's better. Sorry, can you repeat your question?
So he said, well, he congratulated you for the impressive results, and he was wondering if there is any problem if the eavesdropper could attack the signal used for phase compensation.
Well, the intuition there is that I don't think there is any problem from the security point of view, even if I think that more and more people looking into the security of the protocol is always a great thing. But basically, if we attack the signal used for the phase compensation, basically what we're doing is that we're introducing, it's like introducing basically a phase noise on the communication channel. And at that point, what you will see experimentally is that your QBER will go to the roof, because you wouldn't be able to reconciliate your phase encoded pulses anymore. And at that point, basically, you will get you wouldn't obtain a positive secret key rate. So in a way, I think we are in the kind of scenario where QKD does not provide a secure key rate because the channel is not secure anymore in a way.
Yeah, I fully agree with you. So I don't think there is any security problem. So of course, if the system is not working properly, the RQB will increase and you abort. But there is no security issue there. So there is another question from Andreas Pope. Here's a question regarding the evaluation from phase drifts in fiber. And he's asking precisely, do you, sorry, because I cannot read it very well now here. Did you monitor the speed of polarization drift for the same fibers as well? If yes, how comparable are the drift of phase and polarization?
Well, we did monitor the polarization drift in the sense that for our experiments, especially the one obtained at the longest distance, requires several hours of data acquisition in the order of 2 hours and a half, more specifically this one, so the finite size point. So in order to obtain a positive key rate over that time span, we had to implement some active polarization compensation techniques, strategies, which can be found and are detailed in the supplementary material of the paper that is reported here. And in terms of the difference of the drift, of the speed of the drift, well, the compensation of the polarization, I think that I don't have a precise measurement there, but it is more than enough for lab-based implementation, at least, to have a feedback that corrects the polarization every 30 seconds up to 1 minute. And sometimes the polarization will have to be corrected every even minutes and a half or 2 minutes.
Okay. So I have, if I'm allowed, also 2-3 very, very quick questions.
Sure.
One of them is just for curiosity. Just look into this graph where you compare your results that clearly improve previous results, but just that I understand it properly, some of the previous results were in field, isn't it? So, and your results are in the lab.
Correct. So the results that were obtained in the field here are these this point here. Mm-hmm. So the triangle here and the triangle here and the square here. And in fact, you can see the difference between the previous state of the art. This one were the previous results obtained in the lab, and you can see that they tested at the system at different distances and length, while here they only tested the length that they had available on the field. And well, I think that should be noticed here, I think also, is that this point here wasn't actually implemented over 500 kilometers of fiber in the field, but it was actually roughly the same length of this point here in the field, plus other 80 kilometers in the lab as well. So if we're talking about only field-based implementation and looking only at the length of the fiber on the field, these should be probably scaled back roughly here by 80 kilometers. But in terms of comparison between the two, I think it's a very good question, and to wonder if our stabilization system would compare and could work in the field. And this is actually why I talk about the experiment by INRIM, which demonstrated actually the feasibility of this dual band phase stabilization system in the field, which gives, but we are quite confident that it's going to work also in the field. And but nevertheless, I think the two experiments executed in the field by a research group in China are impressive results, and they should get all the recognition, because they really push the limit for field trial QKD by 400 kilometers, basically more than the previous state of the art, which is amazing.
Okay, and then two final questions, but if you can reply them in 1 minute, because I think we have to close the session, but I'm really curious. So the first one is regarding that, of course, you use another phase compensation system. I'm not an experimentalist, I'm a theoretist, so that means maybe my question is very naive. And as I say, if you could be very brief. So intuitively, I have the impression that to compensate by post-processing seems very convenient, although I understand all the features or all the drawbacks that you mentioned by using the same, by multiplexing in time. Do you think, or do you think could be feasible maybe to try to compensate by post-processing by using signals multiplexing frequency?
I thought about it. I think it's possible, but it's very complicated. But this is, I just thought about it. I didn't make any proper simulation and any tests. But the problem there is that if we are going to do that, so basically when you do phase compensation in post-processing, what you're tracking is the instantaneous phase difference between the two arms. At that point, the fact is that if you move the reference signal used for your phase stabilization to a different wavelength, then you will have to be sure what is the phase relation between the two different frequencies. This means that the best solution to this type of problem that I can think of is that probably these two different wavelengths will have to be locked together somehow, probably by a frequency comb type of structure. At that point, you could use one wavelength for the stabilization, and then in post-processing, taking into account the phase drift of that wavelength, and use the other one for the protocol encoding. But then you will, well, first of all, having a stable, ultra-narrow line with frequency comb is very expensive. It requires a lot of very, top-grade research material and equipment. And well, it has still to be proved if it will work effectively.
Okay, then maybe because we are really over time, so I'm going to stop here. Again, Mirko, thank you very much for the very nice talk. I have two announcements. So first of all, if you want to discuss more with the speaker, I understand that he will be available in the Meet Speakers tab, so you can meet him there and ask further questions. And then the organizers, please ask me to remind you that after the break today, there is the business meeting. And maybe you are interested because there will be a lot of information about QCrypt. Also, there will be the prize ceremony for the best student paper. And you can also learn where we will have or where will be QCrypt next year. So, and with this, we conclude and we stop here. Thank you again, Mirko, for the nice talk.
Thank you very much.